Hello everyone, I am Dr. Fawzul Atiq giving some series of lecture for the course Discrete Mathematics. So we are in the unit of principle of counting, and then we have discussed the some basic principle of countings. Among them we learned what is the sum rule, what is the product rule, right? And then the subtraction rule or principle of inclusion exclusion in the previous lecture. So in today's lecture we'll learn few more counting technique. So we'll start with a counting using tree diagram. Now, what is a tree? A tree is basically a graph, right? So that a graph unit will come in the next unit, but tree is basically a graph where you will have some vertices and edges. Okay, sorry, just a second. Where you will have some vertices and edges like this. So this is the vertex. This may be the edges. These are called the tree. This is also, you can say it is a tree till now. So this is, maybe you can say this is a tree, right? And tree is basically a connected graph with no cycle involving it. So suppose in this graph, if I have it like this, then it becomes a cycle, right? Then it becomes a cycle like this. So maybe I can say, so if I move from this, it becomes a cycle. So this is not allowed in a tree. So tree is only a connected one. So you can move from one vertex to any other vertices, and it can be with not having any cycle in it. So that is called a tree. Now, this kind of tree are also sometimes helpful to count some. In case of a counting technique, this kind of tree are also useful. So how to do that? So first, let us see this example. The question is, how many bit strings of length 4 do not have two consecutive ones? How many bit strings of length 4 do not have two consecutive ones? Now, this one, now how to do that? Here it says that it should not have two consecutive ones. So, using the tree diagram, one can easily do that. See, bit string means what? Each characters are of length 4 means there will be 4 length string, and each it's a bit string. That means each characters are 0 and 1, right? So what we'll do, we'll draw a tree by maintaining that two consecutive one should not have. So from suppose for the first position we are checking. Now the first position I can have two options 0 and 1, because then it is not violating the rule of two consecutive ones are not there. So 0 and 1 both can be possible. So I have written 0 and 1 for the first position. Then our next job is for the second position, what are the possibilities you have? Now suppose from the second position, if my first position is 0, then the second position can be 0 and 1 both. No problem at all, right? So I can have 0 and 1 both in this case for the second position. Yeah. But if I start from this one, and how many choices I have? So whose first position, the bit string whose first position is 1, in the first character is 1, what should be the second character? Can it be 1 again? Not possible, because you should not have two consecutive ones. So therefore, you should have only one option, which is 0. So 1 is not allowed in this case. Okay, again, think about the third position. Now it is wherever 0 is there, I can have both the options. 0 and 1 both can happen because I do not have any restriction on it. So 0 and 1. And whenever I have 1, then I have only one option, which is 0. Otherwise, you will have 0 and 1 both. Right? So here I will have only 0. And here this position I have 0. So I can have both 0 and 1 both. So 0 and 1 both. So third position is also filled up. Now, what will be the fourth position of this bit string of length 4? Now, whenever I have 0, I can make it as 0 and 1. I can make it as 0 and 1 both. I have 1 here, so I'll have only one option, which is 0. Here I have 0, so I can have both 0 and 1. It is 0 and 1 both. Then I have 0 here. Again, I can have both the options, 0 and 1 both. So this is 0 and this is 1. And the last one is, I have only one option, which is 0. Now you see that how the strings will be there. Now see, you may write this as 0, 0, 0, 0. This is one bit string. Then another one is 0, then 0, 0, 0, 0, and 1. And then it is 0, 0, 1, 0. The next one is 0, 1, 0, 0. The next one is 0, 1, 0, 1. Then the this one is 1, 0, 0, 0. Next is 1, 0, 0, 1. And 1, 0, 1, 0. So how I made it? I basically have checked this thing. So here, how I made this one, how I made this one, I have just have come through this path. So 0, 0, 0, 0, right? So this is how I made. Now again, how I have made this one, it is 0, 0, 0, and then 1. So I have made this one. Similarly, I have made the other things also. So how I get that bit strings. Similarly, how I made this one how I made. So I start with this 0, 1, 0, 0. This is how all the bit strings of length 4 are made. Correct? And now see, these are all the bit strings of length 4 where we do not have any consecutive two ones. Now see, none of them have two consecutive ones, right? So we have taken all the possibilities. So therefore, how many numbers we have? There are 8 such things we have. There are 8 such bit strings. And what are all the bit string? These are the bit string. These are the bit string which are having length 4 and do not have two consecutive ones. So see, this method not only getting you are counting the number of bit strings having length 4 and do not have consecutive ones, it is also giving you the what are all such bit strings. Correct? So this is how you can use the tree diagram while counting. Yeah, this one we have already discussed. And then I have one more problem, and you can see that this problem you can easily do. How many bit string of length 5 do not have two consecutive ones and do not have two consecutive zeros? Now this one is a very easy one. How to do it? Just see. You should not have two, so just make a tree. The first position is to make the tree, and then the first position you can have both of them 0 and 1 both. But once you have 0 and 1, here the restriction do not have two consecutive ones and do not have two consecutive zeros. So if I start from 0, what a choice I have? If I can I have both the choice 0 and 1? No, no. Otherwise I will have two consecutive 0. So in this case I have only one choice, which is 1. Similarly, here also I have only one choice, which is 0. Right? And in this way, if I continue, because otherwise if I put 2, then I will have I'll violate the rule of not having two consecutive ones and not having two consecutive zeros. So in both the places I'll have only here it is again 0, here it is 1, here it is 1, here it is 0, and 4, and the fifth position I'll have 0 here and I'll have 1 here. So 5 level done. So what are all the bit strings? So here, if I just look at that, there will be two such thing, but what is the exact one? 0, 1, 0, 1, 0. And this one will give you 1, 0, 1, 0, 1. Done. So how many bit strings are there? Two bit strings are there. Again, using tree diagram. So if you have understood that, you can just take this as a homework. This will be a little bigger one, so you make in your exercise book it will take a lot of space, so keep some space and start doing this problem and find out the answer of it. How many bit string of length 5 do not have three consecutive ones and do not have three consecutive zeros? Right, you can do that easily. So this you take it as a homework. Now I will have one more problem. What it says? This problem you can do it using just by using your common sense. Very easily you can do. But because we are learning the tree diagram, so we'll apply the tree diagram thing and we'll count this one. What it says, suppose that hack SRM t-shirt come in 5 different sizes: small, medium, large, XL and double XL. Further, suppose that each size comes in 4 colors: white, red, green and black. Except for XL, which comes only in red, green and black, and double XL, which comes only in green and black, all other have the 4 colors, all other sizes. Then how many different t-shirts are there? So this one you have to count. Now again we can use the tree diagram. Basically how many different combinations you can get. Suppose large size and then red, blue, large size red, large size white, like this. Similarly medium size black. It is different from medium size red. Like that, how many different combinations of mm, t-shirt you can get. So what we will do? We can easily apply the tree diagram method. Okay, just a minute. So here, suppose the first one is the root, and then all sizes we have. There are 5 sizes: small, medium, large. Like this, I have 5 sizes. So I'll have 5 such things. Right? This is small, medium, large, XL, and double XL. So these are the size. Now we'll incorporate the colors. So further, suppose that each size comes in 4 colors: white, red, green, and black, except for XL, which comes only in red and green and black, and double XL, which comes only in green and black. So small comes in 4 different color. So we can write all 4 of them. Right? What are the 4 different color you have? White, red, green, and black. Similarly, mediums also comes in 4 different color. So white, red, green, and black. Large also comes in 4 different color. And what are the colors? It is white, red, green, and black. Whereas Excel comes in only 3 colors. What are they? Excel comes in red, green, and black. So red, green, and black. And double Excel comes in 2 different color. What are they? It is green and black. Now, how many different t-shirt you got then? So 4, 4, 4, 3, 3. So 9 plus 3, 12. Sorry, 12 plus 3, 15 plus 3. So there are 17 number of t-shirts. We have 4, 4, 4, 3, and 2. So there are 17 different t-shirts we have. And what are the all the combinations? Small white size, small size red color, small size green color, small size blue, black color. Similarly, medium size white color, medium size red color. These are all different kind of t-shirts we have. Right? So using tree diagram, one can do in this. But this one, even if you don't apply tree diagram, just by applying common sense also one can do that. But my purpose is to give one more example for tree diagram. Okay. So now we'll come up with another counting technique called the pigeonhole principle. This is also related to the that counting. Right? So what the pigeonhole principle says, which is again you can very easily understand that. If k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least one box containing 2 or more number of objects. So let us understand this theorem through some examples. Suppose I have maybe 4 boxes or 4 pigeonhole, and I have 5 pigeons. I have 5 pigeons. Right? I have 5 pigeons and I have 4 pigeonholes. Now, how these 5 pigeons will enter into this boxes, enter into this hole? So, if all of them are very good friend of each other, maybe all of them sitting in the first one only. Correct? Or if they want to stay comfortably, maybe what they will do? So they may do one they will take. But however, they will take it very one only also. But there are five pigeons are there, and you have only four holes. So even if they take very distributed, very like good way, still one pigeon will remain, right? And that pigeon has to stay in some of the boxes, right? So therefore, if I have four boxes and I have five objects, if I want to place them, then there will be at least one box which contain two or more number of objects, right? Then there will be at least one box which contain two or more number of objects. This is called a pigeonhole principle. Similarly, if I have k number of boxes and k plus one number of object, if I want to place them into k boxes, what will happen? So at least one box will be there which will contain at least two or more number of objects. Clear? This is called the pigeonhole principle. Clear? Okay. Now let us have some example. Now there is a statement. It says that a function f from a set with k plus 1 or more elements to a set with k elements is not one to one. Now you tell me that whether it is true statement or false statement. Now what do you mean by a one to one function? So you have this thing and you have k plus 1 object a1, a2, a k plus 1. And your codomain set having k number of elements. It's maybe b1, b2, bk. Then what do you mean by one-to-one function? One-to-one function means so all of them should have different images. All of them should have different images. Right? Maybe I can write that A2, A3 can go to B2. So like that, even whatever way you do, so if they get different images, then you have k plus one number of elements in the domain set. And you have k number of elements in the codomain set. So how can it possible that all of them will get different images in the codomain set? It's not possible, right? By Pigeonhole principle, at least two of them will be there, which will get at least two of them will be there, which will have image the same element, and which violates the rule of one to one. So it is not possible. So therefore, a function f from a set with k plus 1 or more elements to a set with k elements is not a one-to-one. It's just true statement because you will never find a one-to-one function if you maintain this rule. I hope you understand. Right? So this is a true statement. Okay, read this statement. This one you can again easily understand. Among any group of 367 people, there must be at least two with the same birthday. Why? Because you have 360 days possible maximum in a year, right? So even if you have all students born in a same different day, so how many students different days as possible? 366 days maximum. But if you have 367 people, so at least one day will be there. That will be the birthday of two people by Pigeonhole principle again. So among any group of 367 people, there must be at least two with the same birthday because there are only 366 possible birthdays. I hope this is clear. Then again, look at this problem. Any group of 27 English words, there must be at least two that begin with the same letter. Why? So you have 27 words, English words. And how many English alphabet you have? 26. So even if you have all the words are starting with a different starting alphabet, still how many you can cover? 26 maximum. So at least two words will be there whose starting partitions will be same. At least it should have two. Therefore, you can say that any group of 27 English words, there must be at least two that begin with the same letter. Easy. So these are very easy to understandable thing. Just because of the Pigeonhole principle, one can easily do that. Now, look at this example. Yeah, so look at this example and tell me the answer of it. How many students must be in a class to guarantee that at least two students receive the same score on the final exam? If the exam is graded on a scale of from 0 to 100 points. So how many minimum number of students you need? That you can say at least two students receive the same score. At least two students receive the same score. Then how many minimum number? See, exam is graded from a scale from 0 to 100 points. So if they get all of them are getting different, what will happen? Some student get 0, some student get 1, some get 2, like that. Some may get 100. So how many numbers are there? It's 101 numbers are there, right? Now, if you want to make sure that, if you want to guarantee that at least two students receive the same score, what should be the minimum number of students? So even if you have 101 student and if they get all different, you cannot give guarantee. But if you have 102 number of students, then even if they get different, it is still possible that one score will be there from this, which will be shared by two students, which would be shared by two students. Right? So what is the minimum number of students then? The answer for this question is 102. Right? So that you can give guarantee. I hope you understand this one also. Okay, so yes, as we discussed, because there are 101 possible scores in the final. So by Pigeonhole principle, among any 102 students, if I have, then I can give guarantee that at least two students will score, have the same score. Clear? Okay, I have one more example, which is very interesting one and like very good applications of Pigeonhole principle. What it says, so that for every integer n, there is a multiple of n that has only zeros and ones in its decimal expansion. What does it mean? It means that that has only zeros and one in its decimal. So that means for every integer n, there is a multiple of n, right? There is a multiple, maybe n into k, and that is all it has exists that all decimal expand in its decimal expansion, all entries are 0 and 1. So it may be 0 1 0 1 1 1 0 1 1 like this. So the statement says that for every integer n, for any integer, maybe for the integer 7, then there will be a multiple of n. So 7 into some integer. So this is called a multiple of 7. It should be always there will be one integer in its decimal expansion which are either 0 and 1. So in this case, maybe 0 1 like this I'm saying, or 0 0 0. So all entries are either 0 and 1, 0 and 1, 0 and 1. For any integer n it will happen. How do you prove that? Right? Very interesting and very theoretical question. But you can easily apply the this Pigeonhole principle and you can be able to prove this. So how to do that? Okay, let us see. First, let me move up this one and we'll prove this. Okay. Just yeah, okay. How to prove that? So what we'll do? Let n be any positive integers, right? Let n be a positive integer. Now what I have to prove? I have to prove that there is a multiple of n which looks like that n into k should be written in the form of like 0 and 1, some decimal number which consists only 0 and 1. So what we'll do, this is the first step. Then next, what we'll do, we'll consider n plus 1 integers. What are all that n plus 1 integers? Consider the n plus 1 integers. 1, then 1, 1, 1, 1, 111. So first one is 1, second is 11, then 111, then 1111. Like that, I have n plus 1 numbers, right? So they are n plus 1 numbers. So this is 1, 2, 3, 4. Like this, I have n plus 1 numbers, right? So I consider this n plus 1 numbers. Next is you have already gone through the number theory unit, and if you divide any integer by some integer n, then what are all possible remainder? So suppose I divide some integer I have, maybe it is m, and I divide that integer by a number 5. Can you tell me that if I divide an integer by number 5, what are all possible integers remainder I can have if I divide by 5? So we know the division algorithm. The possible reminders are 0 to 4, right? 0, 1, 2, 3, and 4. These are the only possible reminders I have. So if I divide any integer by a positive integer, so the reminders lies between 0 to that divisor d. 0 less or equal to r less than d. By division algorithm, we all know. Similarly, if we divide by 10, possible reminders are 0, 1, 2, to up to 9. Any integers it can happen. But how many reminder I have? In this case 5, in this case 10. So if you divide any integer by n, how many reminder I will have? N number of reminder I can have. Right? So then our next statement is that if I divide any integer by n, I will have n number of reminder. So that part we will incorporate. So I'll write down. So the next part is there are, sorry, yeah, just a second. So I'll write down that observation now. So there are n possible reminder, n possible reminder, n possible reminders when an integer is divided by n, is divided by n. Now see, we have understood that there are n possible reminders are possible if we divide an integer by n. Now, in this above this n plus 1 numbers I have now, if I divide all of them by n, my reminders are only possible reminders are n. So if I divide one by one, and if I'm getting all of the reminders are different, but I have n plus 1 in numbers and possible reminders are n. So at least two reminders will be same. If I divide all of them by n, so at least two reminder will be same because I have n plus 1 maximum number and maximum reminder is n. So by Pigeonhole principle, I have at least two numbers are there. For that case, if I divide them by n, I will get the reminders the same, right? So that part I can get it by using the Pigeonhole principle, right? So there must be two. There must be 2 with the same remainder, when divided by n. That means when we divided this number, this n plus 1 number by n, there must be 2 with the same remainder by Pigeonhole principle. Now, how these numbers are looking like? So if I just apply suppose two numbers are there, which are maybe of this one, which is if we divide by n, so that by division algorithm, I can write this one is equal to n into, so some maybe k into n plus r, and another number maybe again 1111 is equal to k1 into n plus r, because they have the same remainder. And then what you can say, if you subtract one from the another one, what you will get, if you subtract the bigger one, lesser one from the bigger one, so these two integer I have, right, these two, where if you divide by n, you will get the same remainder. So suppose the first one is the bigger, so if you subtract from the first one to the lesser one, what will happen? This side, whatever digits I'll get, it is either 0 and 1, right? It is either 0 and 1, right? Correct? And this side, what will happen? It is k minus k1 times n, because r will be, because they have the same remainder. So this is this into n. But what does it mean? So this side, it is a multiple of n, right? K minus k1 into n, it is a multiple of n, and that is equal to the number which all entries are either 0 and 1, either 0 and 1, because you subtracted this from this one. So that number is in its decimal place either 0 and 1, and that will be always is a multiple of n. So n is any particular element. So we can easily say that for every integer n, there is a multiple of n that has only 0 and 1 in its decimal places. Right? So this proof is done. So the formal proof is here. The formal proof is here. That's what we have discussed. And let me end the lecture. All the content I have taken from this book only. I hope these videos are helpful for you. I hope you have enjoyed the lecture. If you like the video, please click on the like button. And if these videos are helpful, you share with your friends so that they can also get the benefit. And please do subscribe my channel. It will motivate me. It will also helpful for you, because there is another series of lecture called probability and statistics that will also be helpful for you. If you have not done, if you have not subscribed yet, please subscribe it. Thank you very much. We'll come up with the next video in the next lecture. Thank you. Bye-bye.